All right. So our last speaker of the day in terms of the papers will be Evan Donahue, who's at the University of Tokyo. And he's going to be presenting on very interesting work on using goals as constraints in miniKanren. Obviously, we have many types of constraints. And so it's interesting to see an alternative approach to implementing constraints. After this, we'll have the coffee break. And then after the coffee break, we'll have a discussion on what the future for miniKanren relational programming might look like. And I hope you all just join us for that discussion. Okay, Evan, take it away.
All right, thank you. Hopefully you can hear me. If not, someone jump in and let me know. I'm going to try to share my slides now. Keep your fingers crossed. All right, so we just got one share button, so let's click that and presenting. Hopefully you should see the slides. If not, flag me down. All right, let's get going. So, as Will mentioned, my name is Evan Donahue, and I am currently a postdoctoral fellow at the Tokyo College Institute for Advanced Study at the University of Tokyo. My talk today is entitled Goals as Constraints, Writing miniKanren Constraints in miniKanren. And in it, I'd like to talk about some work I've been doing trying to make it easier to express complex constraints in miniKanren and still have them run efficiently. I've divided today's talk into three sections. The first one, I'd like to describe the interface to the constraint system and what it would look like to program in this dialect of miniKanren. Go through a few examples. Next, I'd like to talk about the implementation, which I think I can simplify enough to basically give you the whole idea of how to do it in this talk. And then finally, I'd like to talk a little bit about the issues I'm currently working on and a little bit about performance and kind of the current state of the system, which is a little bit of a work in progress, but I think is far enough along that we should have plenty to talk about. So let's get started. In comparison, so many non-trivial miniKanren programs require some form of constraints to run efficiently. And the problem is that each new constraint generally requires, all else being equal, extending the miniKanren implementation itself, which means that only implementation maintainers can really add new constraints. There has been a few examples of work in the past that have created constraint authoring frameworks, which make it easier, although it still does require time and a degree of specialized expertise to author new constraints. And moreover, I would argue that there are some potentially desirable constraints, the sheer complexity of which is beyond what it's realistic or feasible most of the time to express in such frameworks. So in the limit, and this is a slightly beyond what we can do at the present implementation, although hopefully not by very much, if we imagine all the way at the extreme end, implementing something like an entire relational interpreter as a constraint, that's a whole order of complexity above something like Absento, and that's what I'm aiming to be able to do with this implementation. Because I think that could open up some really interesting new architectures for relational interpreters and other related types of programs. I wanted to bring that up as an example in particular so that we could think about what would be required for that level of undertaking. Right? We wouldn't want to implement a relational interpreter entirely in scheme code or in the host language code because that's what we have miniKanren for in the first place, right? And that's exactly the idea of this talk. So if we view constraint solving as search, then the constraint solver is just another miniKanren interpreter nested inside miniKanren, and we can use that to express things that miniKanren makes it easy to express over and above writing our constraints in Scheme or another host language. I think miniKanren is an ideal constraint language for miniKanren because now we can express constraints over the same kinds of structures that we can generate, and even potentially reuse the same code to do both in a single program. So in order to do that, we're going to need three new forms for constraint authoring. Constraint, which wraps an arbitrary miniKanren goal and specifies that it runs as a constraint. P-constraint, which defines new primitive constraints. So normally unification is the only primitive constraint, the base system. But if we need to constrain some infinite quantity like symbols or real numbers when writing symbolo or numbero, we can define a new P-constraint, which works similarly architecturally to other constraint authoring frameworks in the sense that we fall back to Scheme or host language code to do what we can't express really in miniKanren. And then notto, which is a simple form of negation, which helps us write a whole new set of constraints. All right. Let's look at some examples of the constraints we can write with these new forms, starting with Booleano. So here on the left, we have a normal generative miniKanren relation Booleano that just enumerates true and false. And on the right, we have the constraint version, which is just the normal version wrapped with constraint. So this works exactly like you'd expect. If V is ground, then we fail or succeed right away. And if it's free, we suspend in the constraint store. And then if V is ever constrained to be not true or false, a disquality, it immediately unifies with the other one. So this is, note that this implementation, this whole implementation of miniKanren that we're talking about here is a first order miniKanren. So constraint is not really a syntactic form per se. Condy is going to return a concrete Condy goal structure, and constraint just accepts that as a function argument and wraps it in a constraint structure, so that we can also just write the normal relation and turn it into a constraint at the call site like so, which is useful if both the constrained and unconstrained version are important. We can extend that pretty naturally to something like a simple arbitrary finite domain, just dynamically building a disjunction of unifications that are over all the domain elements and running it as a constraint. So note that in all cases, when we see in this talk, when we see the double equals unification there, we're referring to the fully general normal miniKanren unification. So we can have free logic variables just about anywhere you want in these constraints. We can also handle recursive structures like lists, as in proper listo. As a normal relation, this generates an unbounded number of lists, but running it as a constraint, it simply runs until it hits a free variable in the tail, and then it waits, suspends itself and waits in the constraint store. And then when that becomes bound, it continues constraining. The problems like this show up frequently in normal miniKanren, such as in relational interpreters, constraining lists of arguments to lambdas to all be symbols, or testing whether something is a valid number with one of the usual miniKanren numeric representation schemes without having to generate a bunch of numbers spuriously. So it's a very natural thing to express these relations in miniKanren, and constraint just lets us get rid of that middle step where we generate all those useless numbers, which frequently makes what we want to express somewhat awkward to express in unconstrained miniKanren. Now, one minor limitation I'll flag here is that if the constraint, since the constraint itself never fully grounds the tail of the list, so if we never ground it ourselves, the reifier shows us this sort of ugly constraint on the tail instead of a fully proper list. But I think that's probably a minor implementation issue we can fix in the reifier. That's one of the loose ends I'm kind of currently working on tying up in the code base. So another thing I wanted to flag in this example before it becomes important later on is that I actually rarely use fresh in this code base. Instead, when I need to structure a pair, I use a pattern matching form more like this. Matcho binds L to the pair of free variables H and T, and it runs its goals in the lexical scope in which those free variables are bound. Matcho is proven much easier to optimize than fresh, especially in the context of this constraint system. So I'll sort of mostly be talking in terms of that. And I think actually, fresh is not currently implemented in the classic sense for compatibility with this constraint system, although I've done it in past versions of the code base, and there's no problem with it. It's just a sort of current state of the code base comment. And then finally, we get to presento. So you can think of presento as the negation of absento. So rather than saying a value must not be anywhere in the term, presento says the value must be somewhere in this term. And the implementation is exactly what you'd expect from that description. Either the term unifies with the value, or else it's a pair, and either its head or tail contain the term. The thing that makes this such a pain to implement in traditional constraint systems is that, unlike absento, we can't simply check the presento constraint on our head and tail independently. If the value is present in the head, then the constraint on the tail must not cause the branch to fail, even if it would otherwise, right? So there's a dependency between them. What we have to do instead is implement a single constraint that walks the tree, and whenever it comes to a free head and tail in a pair, it has to suspend itself on the head, but remember the tail for later, in case it fails somewhere down inside the head and has to jump back to an earlier tail to keep walking the term. So as it walks the tree, it may build up an arbitrarily large list of unvisited branches that it needs to finish visiting to confirm that the value is somewhere in one of those branches. However, our misery isn't over there, because what if we want to check that a complex tree term is present inside another complex tree term where both of them may contain free variables, right? So now we have to suspend ourselves on some collection of the variables within that unification. And then only once the unification fails on one of those subterms do we want to resume the higher level walk of the tree. So all of this is doable in a sort of Turing complete anything is doable sense, but it's just really obnoxious to write. So I think anyone who's tried to write presento can probably attest. As we'll see when we get to the implementation section, What we're looking at here is essentially just a disjunction of conjunctions, and we can handle that in a principled way without having to re-implement it for every new constraint. The next two sections are a bit shorter. P-constraint just lets us define basic constraint types other than unification to use inside our freshes and condis. It's useful for dealing with non-enumerable host system values like numbers and symbols, and we need it to implement things like symbolo and numbero in a sane way. So mechanically, it works a lot like previous constraint systems in that you have to define what happens to bound values and interactions with other p-constraints manually in whatever your host language is. Although crucially, you don't have to define its relationship to other complex constraints, right? So symbolo and numbero will never have to worry about absento or anything else that's written with the combinators because those are already handled automatically in the system. We only need to worry about other p constraints like unification and other symbolos and numberos and whatever else we've defined with p constraints, because as long as we handle those interactions between primitive constraints, the system will automatically parse absento and whatever else into its component unifications and p constraints and test the interactions individually as needed. So let's see here. Looking at this code, which just defines a generic typo constructor for type constraints, we first just check whether v is ground and then return a trivial succeed or fail goal if so. But if it's a variable, we use the p constraint constructor. This creates an object with three properties, which is a list of variables on which the constraint depends. So here, list v, a reference to the function that handles the checking of constraint satisfactions, in this case, type check, and a list of auxiliary values that get past the type check, which in this case is just our predicate function t question mark, which might be symbol or number, pair, or whatever predicate from the host language would be passing in here. So we can then define all of our type constraints in terms of typeo. I'm not going to show type check as it just sort of currently requires little knowledge about the underlying system architecture and probably needs an API redesign if I'm being honest, but basically just receives either a value to which v is bound or else another unification or primitive constraint bound to v and then has to return succeed, fail, or another primitive constraint that's a simplification of the current one and kind of just works on in the host language in that way. You just define a function that does that for that particular return signature. So finally, that brings us to Nado, which lets us negate arbitrary miniKanren goals and constraints. So disequality is just negated unification, and that's exactly how it's implemented internally. And Nado sort of structure wrapper just wraps around the primitive unification constraint, first order constraint. We can similarly define other negated primitive constraints the same way. Nado just creates a structure that wraps whatever primitive constraint in a Nado container, and that gets handled by the interpreter. And we can even handle complex relations as well. So negated conjunctions and disjunctions become disjunctions and conjunctions of negated constraints via De Morgan's laws, as you would expect. To negate fresh and lista, we really just run fresh normally and then negate whatever goal comes back, like any other negated constraint. I've only tested this negation of the pattern matcher. Like I said, fresh isn't completely supported enough yet for me to have tested negated fresh, although I think in principle it would work the same way. But yeah, and we can also sort of implement absento and presento in terms of one another by just negating them if we wanted to do that. As I don't know if there's any particular limit to this as far as I can tell. It works on all the things I've tried it on. And then finally we get to implement absento. So the absent value term is disequal to our complex term, and the term is either not a pair, so we're done, or if it is a pair, our value is absento from both the head and tail. So before I go on, I don't know if we have a good format for asking questions over Zoom, but I'll just check if there are any questions about the interface here before I talk about the implementation, or meta check whether we can even really ask questions in this format. And if I don't hear any response, I'll assume that one of the answers to those is logically a negation, and we will continue with the implementation.
I don't see any questions online, but there might be some questions in person. And if not, I have a question. So my question is, if you go back a slide or two, for the okay, so for the disequality constraint and also for the not Boolean, but for this disequality constraint, that's fine. The equal/equal. I'm trying to understand exactly what Nado means, because disequality or disunification is not the same as saying two terms cannot unify. It's saying that two terms represent different values. So if x and y were fresh logic variables, then it's fine to say that they're disequal. But if those do unify, so it's not like they don't unify. It's just that they could be different values. So I'm trying to understand what the natto means here.
So what the natto means is basically, and this is kind of one of the things one of my kind of like open conceptual questions with implementation. I'd be kind of curious to hear other people's thoughts on. So thank you for the question. Let me see if I can make that clear what's going on here so we can kind of see where this fits in the kind of greater scheme of logic. But basically, I'll talk about this a little bit later, but what natto does is that there's kind of a very, like a generalized form of the case analysis that we usually do when we implement disequality constraints. It runs its internal goal and then analyzes whether it succeeded, failed, or simplified into a different goal, and then either fails, succeeds, or wraps that in another natto for future negation. So if we run it on unification, it's exactly equivalent to implementing disequality in the way that we usually do. And that the inspiration, I'll talk about this later, but the inspiration behind this kind of whole approach is just generalizing the way we implement disequality to other primitive constraints and other general goals. So basically it does De Morgan's laws to conjunction and disjunction in the obvious way, and then it does the kind of disequality case analysis to unification and other primitive constraints. But there's no, I know like other works have kind of done various sort of deeper dives into negation and quantification and kind of other sort of forms of logic. And this is really just a very straightforward sort of device to implement disequality and disequality-like constraints, which turns out to be seemingly very useful in implementing a lot of common constraints. Does that make sense?
Yes, thank you. Any other questions from the audience? Okay, I think you can go ahead. Thanks.
Alrighty, thank you. Let's talk about the implementation. So the core of this implementation is very simple. I've simplified the code down to use in these slides by stripping out a lot of the performance related details. So I can't guarantee the slide code would run as advertised because I haven't run it, but hopefully it will communicate the key ideas, and then you can look at the implementation or the paper for more details or ask me later. So the way I think about the constraint solver in this implementation at a high level, high sort of metaphorical level, is as a conversation between two miniKanren interpreters, which I call the goal interpreter and the constraint interpreter. So the goal interpreter's main job is to create the branches of the search tree using Conde and Fresh and to assign new constraints to the appropriate branches. When it assigns constraint, it passes control to the constraint interpreter, which simplifies the constraints within a single branch, possibly to failure, and returns control to the goal interpreter. So if we view a miniKanren program as a set of constraints, miniKanren interpreter's job is then to find all subsets of mutually non-conflicting constraints logically entailed by that initial set. So the goal interpreter separates the constraints into all possible subsets, basically, and the constraint interpreter searches for a set of constraints within each subset that does not conflict. So to make this conversation possible, one of the key ideas behind this implementation is that there are no dedicated constraint objects. Constraints are in all cases represented by first-order goal objects. Conjunctions of goals are stored directly in the constraint store. In all of the following examples, just remember it's goals all the way down, right? There are no separate constraints. So let's look at a few of the implementations of some of the main pieces of the solver and see if we can get a working understanding of roughly how they're working. So I've got some scheme code here. Unification will seem hopefully broadly familiar. There are 3 steps, one on each line. Do the actual unification, check for failure, and if needed, continue solving any constraints that depend on the unified variables. So a few comments about this code should hopefully help clarify the interpreter and how it works as a whole. So let's look at the function arguments first. The constraint solver as a whole has the same signature. G is the constraint that has just been added that we're currently solving. So for argument's sake, let's say we're solving the unification x equals 1. S is the current state. CTN is the conjunction of all constraints in the program to the right of G. So let's suppose that before this, we were solving the conjunction x equals 1 and z unifies with 3. The first thing we would do is pull off z equals 3 and any other right-hand goals and thread them through the interpreter as CTN, so we can solve them later, which gets us back to solving x equals 1. So CTN is an abbreviation for continuation, because this pattern just sort of metaphorically feels to me like a kind of continuation passing style pattern. So I've been calling it conjunction passing style, just sort of mentally, even though we're not working with continuations or even literal functions here. I think of the right-hand goals as the future of the computation, and we can actually treat it in ways very similar to a continuation in some circumstances by manipulating it or running it several different times in different contexts, which sometimes comes up in probabilistic implementations, as I think is often done with continuations in other PPLs. So resolve is conceptually an extension of CTN. It's just additional goals that are conjoined into the future of the right-hand solving process. But it is for constraints that started out in the state when the constraint interpreter was called and that have been pulled out so they can be rechecked or resolved, hence the name. So it's important that we keep these separate for reasons I'll discuss later. But for instance, if x was already constrained to be disequal to 2, but then when we start solving x equals 1, now we get pulled out by the unification and added to resolve to be rechecked later, and CTN would be moved to the current constraint to solve. So we move z3 up, we unify x equals 1, and we pull out the constraints on x and we put them in the resolve variable. Finally, committed is a conjunction of all the constraints that have been added to the state so far during this call to the constraint interpreter. So it's the delta of changes made to the state. Since we previously unified x with 1, committed will in this case just be x equals 1, along with any other changes we've made to the state so far. So if we look down through the code for the moment, unify on the first line returns 3 values, the newly extended bindings right here, which are equivalent to the prefix of the substitution in an association list-based substitution. So it's a conjunction of any constraints, it's a conjunction of all the simplified unifications we just made to the state. We have a recheck variable, which is a conjunction of any constraints on any of the bound variables that we pulled out of the constraint store. And we have s, which is the new state extended with the unifications made. So if the unification fails, we return 2 values down here. And the signature for the whole constraint solving function is 2 values here. So one of which is the state, which is the right-hand side failure stream in this case. The other which is a goal, which in this case is the trivial fail goal. And that fail goal conceptually corresponds to committed in the input arguments. So although we're returning a failure here, if we had succeeded, we would have returned committed instead. And the central mechanic that drives this whole interpreter is that we're not only operating on a state, but we are simultaneously constructing a constraint goal, which remember constraints are goals, constructing a constraint/goal that reflects all of the changes that have been made to the state so far. So in this case, if everything succeeds, we'll ultimately return a state with x equals 1 and z equals 3 in the substitution, and alongside it, we'll return the conjunction of those 2 unification goals. So technically, we could probably get away with just returning the delta and not the state. We mostly return the state for performance reasons, but I thought it would probably be illustrative to see both together because they illustrate the same thing, that they kind of represent the same data. And the reason that we need to return the constraints alongside the state is that we may later need to negate or disjoin them with other constraints, which is hard to do with the way that I've represented states. So assume that we do have further constraints to solve because resolve is not yet the trivial succeed goal. Then we would call the top level solver in the third line here with solve constraint, which has the same signature as solve unification here, down here. Succeed goal at the front tells it that we've finished solving the current constraint, and so it can pull the next conjunct off the CTN continuation and solve that. Or if that's empty, it can start solving resolve. And if all of those are empty, then we run out of goals to the right-hand side, and we've finished solving the computation. And if we haven't failed by now, we must have a consistent set of constraints. So we return committed and the state together. Note that bindings here are a reified goal, as I mentioned. They're a conjunction of unifications we've just made to the substitution that we get back from the unifier. So we can join that in this last line to our delta constraint here, the committed constraint, to track the fact that we made these changes for the rest of the program. And we also take any constraints we need to recheck and can join them onto our resolve goal, so they get checked later as we call down into the recursive call there. So if we assume there are no unifications or disjunctions in this particular program, then the return goal and the return state will basically be the same information, and we can just toss out the returned goal and use the state, just like we would be doing in a kind of a normal miniKanren interpreter. That was like a bunch of details there about the implementation. Does anyone have any clarification questions they're wondering about that real quick before I go on? Because that was kind of most of the structure of the interpreter, and the other things are just sort of specification or specializations of that. Get another drink of water while anyone thinks if there are any clarifications they need about
or clarifications needed. I think you can go ahead, Evan.
Already. So now hopefully got some sense of that. We can use that to define the remaining complicated bits of this interpreter. Nado, to further answer our previous question, hopefully. So let's talk about Nado here. G, a little bit confusing in the signature here, but G is actually going to be the negation of the negation. So if we're solving the constraint x is not equal to 1, G is x equals 1, and we're just so we can kind of solve the positive constraint and do our case analysis. So at this point in the code, we've already taken the internal goal out of the negation, and we're solving that for case analysis. And we're just going to try solving the positive version of the goal and doing that case analysis. And this is exactly the way, as I was saying earlier, it's analogous to the way that we normally do disequalities, right? And in fact, this whole system, as I kind of alluded to, came about because I was really just trying to implement a simple type of negation operator. And I was thinking about what it meant to negate a disequality constraint. And since disequality constraints contain all the basic miniKanren logic operators, they have conjunction, disjunction, negation, and unification all packed in there, I realized that we could just straightforwardly generalize the way we handle disequalities to arbitrary miniKanren goals. So this whole presentation you can think of as basically a generalization of disequality handling, and the implementation follows that basic logic. If you understand disequalities, then you can kind of see where we'd be going with this. And the last real piece of this was just realizing that if I then negated the negation, then we would kind of be left with these positive versions of the constraint, like a positive disjunction constraint and unification constraints that were in the constraint store because they were like tucked into disjunctions, but not in the substitution because we couldn't guarantee that they would be constrained in all cases. And then we basically have the full set of constraints that this implementation gives us coming out of that basic disequality case analysis. So just like disequality solving, where we unify these terms, and that where we unify two terms, right, and then we check whether the unification succeeded with these changes, succeeded with changes, succeeded with no changes, or failed, and then kind of either invert or just kind of package it up for later. We do the same thing here for arbitrary primitive constraints. So unification gets handled in exactly the same way that it always does. You know, we either succeed with no extensions, and then in which case we invert to failure, or we fail, in which case we invert to succeed, or we have some extension of unifications that we repackage as a negated disequality constraint and get on with our lives. And similarly, P constraints work the same way in this context as unification constraints. We just wrap them and do the case analysis. You can see that happening basically on the first line where we solve the constraint and get back a state S2, which we immediately throw away, and the constraint C, which is corresponding to the kind of committed that in this whole architecture returns the constraint, the goal representing changes made to S that are present in S2. So C is all the changes we just made solving this positive constraint. We then negate C right there, and we store the negated C in the original state and also in the delta constraint, right? Because we have to track both in the constraint and in the parallel state all the changes we make, and then we continue solving, and that's it. The one remark I need to make here is that it's important, the real only kind of conceptual thing going on with the rest of these relations here is how we manipulate the constraints, the kind of the continuation and delta constraints that we pass to these subsequent solvers. It's important that when we solve G, we need to pass the trivial succeed goals in instead of continuation, resolve, and committed right up there, right? And this is because, as I mentioned, C represents that cumulative delta of all future solving. So if we passed in real goals there for continuation, those goals will show up in their solved forms in C when we get it returned. Then when we negate C, we're not only negating the original goal G, we're negating all the goals to the right, which is not what we wanted, right? So for example, if the goal is x dis equals to 1, then g is going to be x equals 1 in this case, the positive version. And then suppose our continuation is y equals 2 that we're going to make subsequently. Then the return c we get will be x equals 1 and y equals 2 in the substitution. And then if we negate that, we get x is not equal to 1 or y is not equal to 2, which isn't the goal we were solving, right? We were solving x is not equal to 1 and y equal to 2. Right, so we've negated too much. So we have to pass those exceeds in, so we only get the result of solving this one goal, and then we negate that, and we're okay. Likewise, if we passed in the real committed constraint, C would be conjoined to all the past solved goals, and we would negate those, which isn't correct either. So committed is the past conjuncts to the left of G. G is our kind of current conjunct we're solving, and CTN and resolve together are the future conjuncts to the right of G. Right, that's kind of the metaphor we have here. But we only want to negate the result of solving G in our case analysis. So we solve it in its own hypothetical context where all of the others are trivial, and then put that in the store and continue solving, which will guarantee that it's compatible with all future constraints that will pull it out if needed and check it. And condi or disjunction works in a very similar way. We solve the right-hand side and the left-hand side of what I basically, my disjunctions are just binary structures. And then we disjoin the solved forms, conjoin them to our committed delta, and pack them into the state and return. The biggest difference here, again, is that we can feel free to pass in CTN and resolve this time to the solver because we don't need to negate anything. And what we can't pass in, or I think I should say shouldn't pass in, is committed. So think about it this way. Both the committed left-hand side and CRHS committed right-hand side there contain all the changes made to the state within their respective solving processes. So if we pass committed into them both, which represents the whole past of the computation, then both will contain copies of committed. This essentially distributes the past conjunction over the disjuncts and yields multiple copies of the same constraints, which isn't technically wrong. But my informal experiences so far have convinced me that what we really want to do is factor out as much as possible from the disjunctions to get good performance. So you'll notice instead of disjunction, or you get disjunction constructor, I use dist factorize there to combine the two disjuncts. And all that does is just normal disjunction, plus it searches all the disjuncts for identical constraints that are common to all disjuncts. It factors them out when possible. So if x equals 1, x unifies 1 shows up in every disjunct, then we just write x unifies 1 and the whole disjunction. So the key thing to note here is that we never add the disjunction back to the state. That happens only at the end of the solving process, and that's important. I've been referring to this constraint solving approach as a kind of search, but here's where that actually becomes apparent, because without disjunction, search is kind of a little bit trivial, right? So you can think of what we're doing here conceptually with this whole solver as taking all of the disjunctions out of our constraint store. And this is kind of a naive, simple version that we're doing a little more efficient than this, but you can think of it as equivalent. If we took all the disjunctions out of our constraint store, so now we have a state that is purely a conjunction of equalities, disequalities, type constraints, whatever. And let's imagine that so we have some disjunctions here. Let's imagine that the first line is one disjunction we pull out, and the second line is a second disjunction. Then each disjunct individually is kind of a contained disjunct goal. Then to the extent to say that we're searching these constraints here is basically saying that first we would take our state, we pulled out all these disjuncts, and then first we're going to add disjunction 1, 1 to our state and make sure it doesn't fail, make sure it's consistent. And if it is, we add disjunction 2, 1 to our state. And let's say that fails now, maybe it conflicts with disjunction 1, 1. Okay, well, we back out. It's a depth first miniKanren search. We add disjunction 2, 2 to our constraint. And eventually we're going to find one disjunct in every disjunction that doesn't fail. Otherwise, everything fails and we just return failure. And then we can stop at that point if we want and pack all of these disjunctions up without their failing disjuncts into a goal, and stick that in the constraint store, kick it back to the goal interpreter, and get on with the search, the global multi-branch search. The code I presented here, this sort of simplified disjunction code, isn't going to do any early stopping. It's going to search all the branches of everything, but you could potentially stop early. And there are kind of various ways you could do that. And that's kind of one of the big things I'm working with now is exactly how lazy to be and whether it's worth it and whatnot. But if we wanted to stop early, we'd change our last line to something like looks like this. What this is doing is essentially conjoining the continuation, right, all the future constraints, the right-hand side, to the unsolved right-hand side of the disjunction, and then disjoining that with the solved left-hand side. And this is exactly analogous to how the normal miniKanren search will bind a goal to an incomplete stream, incomplete right-hand stream, which implicitly conjoins it with all the subsequent answers that stream produces. Right, so we are binding the continuation constraint CTN as the yet unexplored stream represented by the right-hand side of the disjunction. And we also don't need to worry about divergence because fresh or macho in this case is going to stop expanding when it runs out of ground terms before we have to start speculatively binding free variables and such. And with macho, what the pattern matching is, that's very trivial to do. You just check if there are any free variables in the pattern, in the variables you're pattern matching, and then pause if there are. Fresh is a little more obnoxious. You have to check if you get any disjuncts back when you solve it, but you can conceivably do it in an analogous way. And the final thing that we have to talk about are attributed variables. So by which I mean this is the practice of storing constraints in the constraint store indexed by the variables on which they depend. So we only have to recheck a constraint if one of its variables has been modified. So putting x is not equal to y in the constraint store, for instance, will often in many implementations, including previous ones, the previous versions of this code base, will create two entries in our constraint store indexed by x and y respectively, right? And once we solve a constraint, once we solve a constraint, we need to figure out which variables it depends on and copy it to all of those variables in the constraint store. So for most constraints, this is easy. Unifications depend on all their variables. Negations and conjunctions depend on all the variables of their children. One caveat there is that since the constraint store itself is implicitly a conjunction of the constraints it contains, if we want to store a conjunction directly, we can just store all of its children independently, and they're implicitly conjoined. And then the disjunction is the tricky case, because if we solve all disjuncts as we do in the simple case above, we could make it depend on all its children. But depending on our objectives, we could also get away with less, which is kind of what I'm currently working on. How much of the disjunction do we need to solve / do we want to solve? And then we have to sort of store an appropriate number of disjuncts in the store. So to wrap up this section, those are the main implementation details. I haven't really touched on fresh too much, like I mentioned, but the pattern matching case is straightforward, mostly because I don't have a reference implementation anymore of the normal fresh because I haven't kept that updated with the architecture. So I think we'll probably need classic fresh in order to like rate the sort of constraint I'm hoping for, like a constraint that's a relational interpreter, but I'm currently sort of exploring that, like I've been talking about. Let's see, I think this ends at 7:30, so I'm going to skip a discussion of solving levels here. I'll come back to it if people want to hang around, or I don't know how we're doing that. But basically, it's just me kind of ruminating about how lazy to be with how many disjuncts we solve, because we don't need to solve every disjunct to guarantee failure, to guarantee we don't fail. But if we don't solve every disjunct, we have stale variables running around, and that becomes tricky to analyze. So there's just some trade-offs there that I'm currently working through, is the basic summary. I have a few performance benchmarks that I've been keeping that are kind of unofficial. I haven't included them in the paper just because they're not super scientific at this point. But I can just share them here as a general sense of where the code is at the moment for people. So these are benchmarked against faster MK, which is the implementation that I'm sure many people are familiar with. Both of these implementations are in Shea scheme, so it's at least somewhat comparable in that respect. Of course, there are many differences between them, and so exactly what can be attributed to the constraint differences and what to other random details is kind of requires further analysis. But just at a high level here, so these are a bunch of disequality related constraints, and I'd have to kind of more time could get into like what each one is testing, but it's just kind of a handful of disequality benchmarks. And on the right hand, we have the percent faster than faster MK, if indeed faster. And the way to read that is that 84 in the middle there would be that faster MK takes 184% of the time. So positive numbers mean faster, negative numbers mean we're kind of slower. And in this case, disequality is faster in all cases. There are some some possible reasons for this aside from just writing bugs in the testing code or something, which is always possible. Just speculating here, but so there's some basic differences in like how the constraint stores are optimized that may come in. So like this implementation stores constraints directly in a substitution, which kind of saves you a bunch of walks. There's no separate constraint store. Since it has a separate unique index for every variable, we only have to store disequality constraints on one instead of both free variables if needed. Things like that. It could also just be that these tests the access pattern happens to be better for the substitution data structure I have in this implementation than the one in the FasterMK, and that a different test would have a different access pattern. But there is one important difference here that I can attest to, which is that there's a slightly different meaning between the way I've implemented disequality here at FasterMK, which is that I've implemented disequality lazily. So if you look at that penultimate test there, laziness, if we check there's a special lazy unifier that I use for disequality. So if we check the first disequality primitive check and that doesn't fail, we know the whole thing won't fail. So I just wrap the list up in its own disequality constraint and return without checking the rest of the list. So whether that's net gain, net positive, long run, still sort of waiting for experience to teach that. But for a simple test, it leads to kind of hilarious numbers that, are just testing a lazy versus an eager implementation, of course. And then Absento, it's a little more complicated. I have two tests here. The first one tests, removing and replacing one constraint by unifying it with pairs with one variable free, and the second one is expanding all the trees in the store by unifying with two variables free. Slower in the first case, faster in the second case. Don't have any great theories about that aside from just differences in the constraint store optimization, maybe handling better the expanding collection of absentos. I'm almost certain that the implementation of Absento itself is not faster than it is in FasterMK, just because it's sort of composed of those three constraints, which is sort of three potential lookups. But this is kind of just me speculating. They're just sort of internal performance benchmarks I use to kind of test regressions in the code base. So I don't have any strong claims to make about them, but that's just kind of what I'm looking at. So here it is, and make your own interpretations, I suppose. And with that said, I think we're pretty much out of time. We're a couple of minutes long. Sorry about that. And here's a link to the GitHub. I tried to hastily scrape together some documentation last night that would just basically orient people to using it, but feel free to take a look at it. Let me know if there are any bugs. I'm hoping to sort of maintain this as a sort of fully featured miniKanren implementation for future research, and perhaps for anyone else who is interested in these things, or hopefully can integrate my probability work as well soon and get to work on that. So feel free to look around. Let me know if there are any issues. Happy to answer any questions at this point if we have time, or just call it there, and looking forward to the discussion later. Thank you.
All right. Thank you very much, Evan. Let's thank our speaker. We're starting to get into the break, but I do have a question online from Greg. Question for Evan. Is there support for efficiently checking satisfiability across combinations of possibly even different types of constraints? For example, will the system recognize the unsatisfiability of a conjunction of these constraints? Boolean X, Boolean Y, Boolean Z, all different X, Y, Z, or otherwise unconstrained X, Y, and Z. So that sounds like a sort of finite domain type of things, where if you had finite domain solver, you could prove that there's no satisfiability. But would you be able to do that with your constraint approach?
I would have to look at that in print and or possibly run it to be certain. My guess is that there's a good chance that we're handling the kind of thing you're describing, just because of the way that I described the search. What we're really doing is we're looking for some. So in terms of unsatisfiability, I'm a little more confident. In terms of if we're looking for some subset of disjuncts that can all be compatible in the same state. And so we're going to kind of, basically in the limit, just iterate over all combinations of true and false for all the variables you've constrained. And as long as there's some satisfying collection of those, we'll succeed. And if there's not, we'll fail. And then moreover, if we also solve aggressively enough to try to look for situations where we don't necessarily fail, but we can commit unifications. And I've tried to make at least those two pillars pretty robust in terms of if the constraint SOAR implies failure, we should fail if it's unsatisfiable. And if the constraint SOAR implies a unification across all disjunctions, we should extract that and unify it. If there are gaps in the reasoning, I don't know. Please test it and tell me, or please send me a description of a test and I'll test it. But my guess is that probably if it's an unsatisfiability question, we should solve that.
Okay, thank you very much. Let's thank Evan one more time.